forced air system airflow rate, fan watt draw, and determination of fan efficacy. So these are the references for this particular section. It's going to be reference appendices in section RA 3.3. And again, that's the link where you can download the actual document, or you can also download it from the LMS. Improved system airflow rates, or CFMs, and reduced fan power and watt draw is achieved through improved air distribution system design, including more efficient motors and ducts that have less resistance to airflow. These designs and verification criteria are applicable to ducted, split, and packaged space conditioning systems serving low-rise residential buildings. Determination of fan efficacy, watts per CFMs, utilizes simultaneous measurement of air handler fan watt draw and airflow rate. So basically, the purpose of this test is to make sure that the systems are not using any more energy than they have to per CFM being produced by the actual system. So the overall training goal is to gain an understanding of forced air system airflow rates, fan watt draw, and determination of fan efficacy testing equipment, protocols, and forms. And these are the sections that we're going to be covering in this particular PowerPoint. So let's go over the equipment specifications first. Just like everything else, we had equipment specifics that we have to use and certain type of equipment that we can or cannot use, and this will be covered. Pressure measurements shall be measured with equipment having an accuracy equal to or better than plus or minus 1% of pressure reading or plus or minus 0.2 pascals, whichever is greater. All pressure measurements within the duct system shall be made with static pressure probes such as a Dwyer, A303 or equivalent, and that's the picture of a sample probe. And these are the same probes that we talked about earlier when we were talking about duct flow and airflow. Airflow rate measurement shall be made with an airflow rate measurement apparatus, which is the sensor plus data acquisition system, having an accuracy of plus or minus 7% of reading or plus or minus 5 CFM, whichever is greater. On the left-hand side, you'll see the 4 different pieces of equipment that you can use to measure airflow. On the top left-hand side, you'll see the duct blaster, which I've covered for the purpose of the duct blast in the previous section. Nonetheless, the duct blaster can also be used to measure airflow for this particular test. On the top right-hand side, you'll see the flow grids. On the bottom left-hand side, you'll see a powered flow hood. And on the bottom right-hand side, you'll see a regular flow hood. We're going to be covering the procedures on how to measure the airflow with each one of these pieces of equipment. Fan watt draw measurements shall be made with true power measurement systems, i.e. sensor plus data acquisition system, having an accuracy of plus or minus 2% of reading or plus or minus 10 watts, whichever is greater. And on the right-hand side, again, there are 2 different types of equipment that you can use. Now, the piece of equipment on the left-hand side, that's the kind of meter that you would use when you have a hardwired system. If you have a hardwired furnace, obviously you're not going to be able to unplug it and plug in a watt meter into it. So by hanging that meter on top of the line itself, you're going to be able to take a watt reading off of it. On the right-hand side, that is a plug-in watt meter. And those are for units that are actually plugged into an actual outlet rather than being hardwired into the house. And for those, obviously, you can unplug it, plug the meter into the outlet, and then you plug the unit into the meter and taking a watt reading that way. Either way, they're both approved for use. As I mentioned a couple of slides ago, the system airflow rate shall be measured using one of the following type of apparatuses. So we have the fan flow meter, which is the duct blaster, the flow grid, the traditional flow capture hood, and a powered flow capture hood airflow measurement device. We're going to be explaining how to collect the data with each one of the systems once we actually get to procedures. So the first one is the fan flow meter or the duct blaster. So it shall consist of a duct pressurization and flow measurement device and a static pressure measurement device meeting the specification as previously described. On top, you'll see the Minneapolis. The bottom, you'll see the Retrotec, just like the duct blaster systems that we discussed in the duct leakage section. The airflow grid shall consist of an approved flow grid and a digital pressure measurement device that meets the specifications as previously described. So in this particular case, you're looking at the Minneapolis or Energy Conservatory flow grids. The flow grids are very specific in the type of equipment that they are. The manometer that you see in the picture is the same manometer that's also used with the duct blaster. So the duct blaster manometer is used with a variety of different equipment. Here we have a traditional flow capture hood. It shall meet the applicable instrumentation specifications previously described, and it may be used to verify the system airflow rate if it has a capture area at least as large as the system grill in all dimensions. So basically what that means is the fact that the top area of the flow hood has to be able to completely cover the return grill that it has to cover, that's going to be measuring. If it doesn't, you either have to build or buy an adapter to make sure that the flow hood will cover completely the return grill that you're testing. The powered flow capture hood airflow measurement device is a device that has the capability to balance the flow capture static pressure difference between the room and the flow capture hood enclosure. It meets the applicable instrumentation specifications as previously described. It may be used to verify the airflow as long as a flow capture area at least as large as the system register grills in all dimensions, just like the traditional flow hood. The fan adjustment needed to balance the flow capture static pressure difference shall be provided by either an automatic control or a manual one as well. So as you can see in the picture on the left hand side, that is actually a duct blaster fan with the same manometer with an additional attachment piece used specifically for this particular test. For watt draw, the watt draw measurement shall be measured using one of the following types of apparatuses. You have a portable watt meter, an analog or the analog utility revenue meter, or the digital utility revenue meter. The portable watt meter shall consist of a watt meter meeting the applicable instrumentation specifications as previously described, and we talked about this in a couple of slides ago. The analog utility revenue meter shall consist of a utility revenue meter meeting the applicable instrumentation specification as previously described and a stopwatch that provides measurements in units of seconds. And you'll see what you need the stopwatch for once we actually get to the procedure. The digital revenue utility meter shall consist of the digital utility revenue meter meeting the applicable instrumentation specifications as previously described that provides direct digital display of the watt draw. So now let's talk about procedures and how we actually measure the airflow and the fan watt draw with the equipment that we just described. Before we start talking about the procedure, let's talk about the exceptions to this particular test. So the airflow rate, fan watt draw, and determination of fan efficacy is not required when any of the following conditions apply. Either the system is not ducted or the system does not have air conditioning. And keep in mind that non-zone systems may install return ducts and grills in accordance with Table 4-10 and 4-11 in the Residential Compliance Manual, or 150.0C and 150.0D in the standards, in lieu of conducting the adequate airflow and fan watt draw test, as previously discussed in the Title 24 overview section. There are two procedures that we will discuss in this section: the system airflow rate, which you may also hear referred to as the adequate airflow, return adequate airflow, and the fan watt draw. The system airflow rate for systems utilizing an intentional ducted ventilation airflow from outside the conditioned space into the return system. The outside airflow may be included in the system airflow if that flow occurs in all operating modes of the HVAC system.
For multi-zone systems that utilize a single speed compressor, the airflow must be measured for each and every operating mode of the system. This must be accomplished without bypasses from the supply ductwork to the return ductwork. Now, what do they mean by every operating mode? So for a multi-zone system, you will have two or more zones within the home. For example, a living zone and a sleeping zone, could be an upstairs and a downstairs for a two-story home, but it's going to have multiple zones. So what you must do is you must test it with each individual zone operating. So you would test the downstairs only, then you would test the upstairs only, and then you would do a third test with both the upstairs and downstairs operating. Now, each of those modes must meet the 350 CFM per ton, as well as when you get into fan watt draw, the 0.58 watts. So a little more difficult to do when you have just that single speed compressor. If you have a multi-speed compressor on a multi-zone system, you will test it just like a standard non-zone systems. For all of these, the airflow measurements shall be performed with the fan set at the speed used for air conditioning, which is usually going to be the highest fan speed setting within the FAU.
It can be measured with one of the methods below: the plenum pressure matching method, the flow grid method, the power flow capture hood method, and traditional flow capture hood method. So these are the four methods used by using the four different pieces of equipment that we talked about in previous slides. So the plenum pressure matching method. When supply plenum pressure measurements are used for plenum pressure matching measurements, a 5/16 of an inch or 8 millimeter diameter hole for a static pressure probe, or HSPP, or a permanently affixed static pressure probe, PSPP, shall be provided as shown in figure RA 3.3-1. And this is an example of what those access holes would look like and the location of them. So the hole location shown in figure RA 3.3-1, which is on the right hand side, can be applied to any one of the four sides of the coil box or supply plenum. The hole location shall be labeled Title 24 Supply Plenum Measurement Access in at least 12-point type. Now keep in mind that if for some reason the construction of the house and the location of the unit does not allow for an installer to drill those holes or to have access to those holes due to framing or structural issues, it is okay not to have the holes drilled for the Herzwater, you, basically to see that they're not drilled, but it has to be verified by you to make sure that there is an actual reason of why those holes were not drilled. If the plenum is accessible and the holes are not drilled, that is going to be a failure on our part. So even if the system passes the adequate airflow and fan wall draw, but yet the holes are not drilled in the system will be a fail. So keep in mind that exception when it comes to those access holes in the plenum. And then, as I said, the system that cannot conform to the specifications for the hole location shown in figure RA 3.3-1 shall not be required to have holes. However, if the supply plenum pressure measurement are required for compliance, an alternate location that provides access for making an accurate supply plenum pressure measurement shall be used. The fan flow meter shall be attached at an inlet to a return duct from the condition space with grill and filter removed. If multiple returns are present, block off the ones not being used for this test. Ideally, you'd want to use the main return for this particular test. If the system is not, again, it's not a multi-zone automatic dampen system, the fan flow meter may be attached at the air handler blower compartment door as an alternative. And again, it may be attached. It doesn't have to be attached in such a way. The fan flow meter shall be attached at a point where the airflow through the system will flow through it. When the air handler blower compartment door attachment alternative is used, an air barrier must block the air handler inlet from the return duct system. And that's a example of what we're talking about. So if you are attaching the fan flow meter to the actual blower compartment door, you have to block off the return plenum completely so that air doesn't blow back into the return system. All registers shall be in their normal operating conditions. And then the static pressure probe shall be fixed to the supply plenum at the location previously specified so that it does not move during the test. So the pressure probe will go into the hole that was drilled in the supply plenum. If the fan flow meter is to be connected to the air handler outside the condition space, then the door or access panel between the condition space and the air handler location shall be opened. Place the pressure probe in the supply pressure measurement hole described previously. Adjust the probe to achieve the highest pressure and then firmly attach the probe to ensure that it does not move during the system airflow test. If the probe happens to move or vibrate or shift during the test, it will skew your readings. With the system fan on at the maximum speed, which is the cooling speed, you want to measure the pressure difference in pascals between the supply plenum and the condition space. The recorded pressure is the target pressure to be maintained during the system airflow test. This is the PSP variable that you'll see in the equation coming up in a couple of slides. Attach the flow meter to one of the previously described locations. You want to turn on the fan flow meter, and you want to adjust the fan flow meter until the pressure between the supply plenum and the condition space matches the pressure measured in step 3. So you're going to be equalizing the pressure between the fan flow meter and the actual system. Then you'll record a flow through the fan flow meter. This is the diagnostic system airflow, or QAH, in the equation that you'll see in the next slide. In some systems, system fans and fan flow meter combinations may not be able to produce enough flow to reach the matching pressures due to problems that you might encounter. In this case, record the maximum system flow, which is referred to as the Qmax in the equation we're about to see, and pressure, or Pmax, between the supply plenum and the condition space. And this is the formula that I've been mentioning in the last couple of slides and the variables that we covered so far. So the following equation shall be used to correct measure system flow and pressure, which we've referred to as Qmax and Pmax, to operating conditions at operating pressure, which is the PSP. So the formula is the air handler flow, which is what you're trying to find, referred to as QAH, is equal to Qmax times PSP divided by Pmax to the 0.5 power. So let's look at the variables that are part of this equation. So the PSP, we talked about it. It's the pressure difference in pascals between the supply plenum and the condition space. This is the value that you found in step 3. The QAH is the air handler flow, which is basically what you're trying to find. You have the Qmax, which is the maximum system flow, and the Pmax, which is the maximum system pressure. So let's plug those numbers into the equation and see how it works. So the variables that we have for this example is the PSP, which we have at 20 pascals. You have the Pmax, which is the highest system pressure we're able to measure, which is 19 pascals. And you have the Qmax, which is the maximum system airflow that you can measure, which is 1600 CFMs. So the formula again is air handler flow, which is the QAH. That's what you're trying to find. It's the Qmax, the maximum system flow, which in this case is 1600, times the PSP, which is 20 pascals, divided by the Pmax, which is 19 pascals, raised to the 0.5 power. And this is what those numbers look like. So you have 1600 times 20 divided by 19, raised to the 0.5 power. 20 divided by 19 is 1.05, raised to the 5th power. 1600 times 1.03, and that gives us a final adjusted air handler flow of 1648 CFMs. Airflow is always measured in CFMs. Remember that. We mentioned that earlier. Now we're going to move on to verifying the system airflow by using the flow grids. The supply pressure measurement holes are required as previously described. The flow grid shall be attached at a point where all the system air flows through the flow grid. In order to do so, you'd have to remove the filter and then reinsert the flow grid in replacement of it. All registers shall be in their normal operating conditions. If there are multiple return grills in the duct systems, flow grids may be used to measure airflow at the return grills, but only by installing a flow grid in each return grill and making simultaneous measurements of all return grill airflows. Place the pressure probe in the supply pressure measurement holes previously described. This is the same as we did before during the plenum pressure matching method. You want to adjust the probe to achieve the highest pressure and then firmly attach the probe to ensure that it does not move during the system airflow test. With the system fan on at the maximum speed, which is the cooling speed like we talked about before, you want to measure the pressure difference in pascals between the supply plenum and the condition space. This is the PSP variable you'll see in the equation coming up in a couple of slides, and it's the same as we talked about in the previous equation during the plenum pressure matching method that we covered. The recorded pressure is the target pressure to be maintained during the system airflow tests. You then want to remeasure the system operating pressure with the flow grid in place. You then measure the airflow through the flow grid and the test pressure. If multiple flow grids are present, you want to sum the flows through each of the flow grids. You then apply those variables you collected to the following equation. So the following equation for the air handler flow shall be used to correct flow through the flow grid, which is the Q grid, and the pressure, which is the P test, to operating conditions at operating pressure, which is PSP. So the formula is air handler flow, which is QAH, just like before, equals the Q grid times PSP divided by P test raised to the 0.5th power. And again, PSP is the pressure difference in pascals between the supply plenum and the condition space. QAH is the air handler flow, which you're trying to find. The Q grid is the airflow through the flow grid. If you have multiple grids, you want to add those up together. And then you have the P test, which is the test pressure with flow grids in place. And again, we're going to be using the same variables that we used before, just for a different particular equation. So once we plug those in, we have 1600 times 20 divided by 19 raised to the 0.5th. And again, with the same variables, you're going to be coming up to the same results. So the air handler flow again is going to be 1648. Now for the power flow capture hood method, all registers shall be fully opened, the air filter shall be installed, and the flow capture area has to be at least as large as the return grill in all dimensions. So as you can see for the picture at the bottom, the flow hood capture hood has to completely cover the return grill. That means that the edges of the capture hood have to fully touch the drywall. They cannot be on the edge of the grill, they cannot be touching the metal, they have to fully enclose the register grill. You want to turn on the system fan at cooling speed and measure the airflow of the return grill to determine the total system return airflow. If you have multiple return systems, the total system return airflow, which is the QAH and CFM, shall be the sum of the airflow measurements at each of the system's return grills. That means that if you have more than one return grill, you want to measure them individually and then add them together. For the traditional flow hood capture method, it works the exact same way. All registers shall be fully open, the air filter shall be installed, and the flow capture area again has to be at least as large as the return grill in all dimensions. If for some reason your capture hood cannot cover the whole grill, again like we talked about earlier, you either have to build an extension in order to allow the flow hood to cover the whole register, or you can buy a pre-made extension from one of the manufacturers. And again, you want to turn on the system fan at the cooling speed and measure the airflow at the return grills to determine the total system return airflow. For multiple return systems, the total system return airflow, QAH and CFM, shall be the sum of the airflow measurements at each of the system return grills. Again, if you have more than one return, you measure them individually and you add them up together. And that will be your total system return airflow.
Verification of air filter device design. For all entirely new or complete replacement air distribution systems, the air filter must be inspected to ensure that it meets the design requirements. The design airflow rate and maximum allowable clean filter pressure drop at the design airflow rate applicable to each air filter grill or rack must be determined by the designer or installer and posted on a sticker placed by the installer inside or near the filter grill or rack. So these air distribution systems, when they design them, they're going to design them to be able to achieve this 350 CFM per ton that we're measuring, and this design includes an air filter that's installed. Now the code, as we saw in Title 24, the code's going to require a specific filter to be installed, and the designer can choose the size and depth of that filter to meet those requirements. A smaller, thick filter is going to be more restrictive than a large, thin filter, so they're going to have to design the system with a specific filter in mind, and they're going to need to install that filter as well as label
or apply a label where the filter is installed so that the homeowner or future resident can purchase filters that meet those same specifications. And that's what we're looking for in this part of the verification. So the design airflow and initial resistance posted on the sticker should correspond to the conditions used in the system design calculations. So when they design that system and they pick a filter, that filter is going to have a design airflow as well as an initial resistance. And both those values are going to need to be placed on the sticker, which this is an example of a sticker. It doesn't have to just look just like this, but it does need to contain this information, the airflow rate and the initial resistance. That way, when you purchase a filter in the future, you can purchase one that has these same values. Space conditioning system filters are required to be labeled by the manufacturer to indicate the pressure drop across the filter at several airflow rates. For the system to comply and to ensure adequate airflow for efficient heating and cooling equipment operation, the manufacturer's air filter label, which we can see below, must display information that indicates the filter can meet the design airflow rate for that return grill or rack at a pressure drop less than or equal to the value shown on the installer's filter grill sticker. So what we're going to do is we're going to compare the sticker that the installer placed with the design values, and we're going to compare those to the actual tested values from the manufacturer on the filter label. So what we're going to be looking at here is on the right hand side of the label. The top row is going to be the airflow rate, and the bottom one is the initial resistance. So we're going to look and see, and let's say for example that we had a 900, it was designed for 900 CFM, and it was designed to have a 0.14 initial resistance. So if we look on here at 925 CFM, it's only a 0.13, which is less than the 0.14 at a higher airflow rate. So that value would be better than what the design is. So this filter would comply based on that design criterion. So that's what we're going to compare, is those two values. Now, up until this point, we've been talking about newly installed systems and the requirements and procedures for verifying that they meet the airflow requirements within the standards. Now, we also have some airflow requirements for altered systems. Now, an altered system isn't going to be held to the same standards as a newly installed system because it's made up of older ductwork that was designed to older parameters, and it's not likely to comply with the current standards today. Now, this doesn't apply to all altered systems because we're not going to be doing airflow testing on all altered duct systems. We're only going to be doing airflow testing on an altered duct system for the purposes of verifying it for refrigerant charge. So part of the requirements for the refrigerant charge verification is a verification of the airflow for that system. Now we have different values that are required. So for refrigerant charge, the airflow requirements are going to be 300 CFM per ton for a standard duct system, which is less than the 350 CFM per ton for a new system. And then we remain at 250 CFM per ton for a small duct high velocity system. So the values are a little bit different on those standard systems, but they're the same on the small duct high velocity. Now, because these old systems, they're altered, we really don't have any control over the condition of the ducts. They may be undersized, they may be crushed, there may be just various issues that have been there for many years. So we're going to perform the airflow test. If we achieve either 300 CFM per ton for a standard system or 250 CFM per ton for a small duct high velocity, then it's going to be considered a pass. You document your results and you move forward. However, if you perform your test and you're unable to achieve either the 300 or 250 per ton, there is an alternative method available within the standards to try and get this system passing through the procedures. So what this entails is for the contractor to perform some remedial actions. And this is when the altered space conditioning system fails to demonstrate compliance with either the 300 CFM per ton or 250 per ton required for refrigerant charge verification. And so we'll go through and we'll look at there's 6 actions that the installer shall perform in order to comply with this alternative method.
So first things first, they're going to check to determine that the air filter media is clean. If the air filter media is dirty, then replace it with the clean filter media. The second step will be to open all registers and dampers and remove any obstructions that they might find. They're going to replace crushed, blocked, or restricted ducts if possible. So basically fix any problems with the actual duct system that they might find. They're going to check to determine that the evaporator coil is clean or there are no obstruction to airflow through the evaporator coil. If the evaporator coil is dirty or blocked with debris, if possible, they're going to clean the evaporator coil using a method approved by the manufacturer. They're going to set the air handler fan to high speed for cooling and ensure that the blower wheel and motor are operating properly within manufacturer specifications. They're going to check to determine whether the return duct system or return filter grill size is size too small for the installed system. If the return duct or return grill is size too small, if possible, they're going to perform applicable alterations work on the return duct system or return grill in order to improve the system airflow rate. For each of the listed remedial actions, the HVAC installer shall certify that the remedial action was performed and indicate whether the action was or was not completed successfully. When a remedial action was not completed successfully, the installer shall indicate on the installation certificate the reason the action was not completed successfully. I would like to stress again that you as the refrigerator are not completing these remedial actions. This is for the HVAC installer to complete and for you to verify through the paperwork.
If these remedial actions fail to bring the system into compliance with the airflow requirement, the installer shall complete the refrigerant charge verification utilizing the best airflow rate attainable. So essentially what this means is that regardless of what the airflow result is, you cannot fail this particular inspection. You're going to pass the airflow rate verification for refrigerant charge either by achieving the required airflow or by performing these remedial actions. So as long as one of those two things have been completed, the verification itself will be considered a pass regardless of the actual airflow rate.
The refrigerator shall review the information submitted on the installation certificate and perform follow-up communications with the HVAC installer or the homeowner. The system complies if the refrigerator determines the remedial actions have been performed and the information reported on the installation certificate is valid.
If the system complies through the use of remedial actions, the system cannot be used for sampling.
So there are different reasons that you might see low measure system airflow, and these are a couple of things that you diagnose quickly in the field. So the fan setting might not be set on high when testing. Again, you gotta have to test the system in the highest setting possible, and generally speaking, it is the cooling system. Now, something to think about, if you're conducting this test during the winter and the temperature outside is less than 60 degrees, if you're going to turn on the air conditioning system, it might be a good idea to disconnect the actual condenser. If the condenser actually comes on and it's below 60 degrees, you run the chance of freezing the lines, and in that case it's going to permanently damage the compressor. So if you're below 60 degrees and testing for this particular test, meaning that you'll be turning on the cooling system, which is the highest speed setting for the system, pull the disconnect on the condenser first so that the blower will run at the highest speed, but the condenser will not kick on. And then obviously remember to turn it back on when you're done with the test. Another reason for this particular test to fail, or reason for low measure system airflow, is return duct leakage. In the picture on the right hand side, obviously that's an extreme scenario. It looks like you have a whole return duct just disconnected. But nonetheless, leaks in general will affect your system airflow, and especially return duct leakage. Another reason could be damage or blockage to return ducts. So as you can see, you have crimped ducts. Obviously, if you have a duct that's crimped, collapsed, disconnected, whatever it may be, you're gonna see low measure system airflow. So it's another item of interest. And also oversized, undersized return ducts and or return grills. So this is really just a design item. If there was a problem with the way the system was designed in regards to undersize or oversize return ducts or grills, there's not much that you can do. Nonetheless, if the system fails, the system fails. But if you check for everything else that we talked about and you cannot find anything, it might be a design issue. So at that point, they would have to go back to the design stage and figuring out whether the system was actually installed properly into standard and or was designed properly to begin with. And now we're going to move on to fan watt draw. So the fan watt draw can be measured with one of the following methods. You have the portable watt meter, or then you can use the analog utility revenue meter or the digital utility revenue meter. When taking the reading for the portable watt meter, first you want to have the registers being fully open, and the air filter shall be installed. You want to turn on the system fan at the maximum speed, which is usually the cooling speed as previously described. Include the outdoor air introduction if the ventilation is provided through return duct system. So if you have a CFI system, ventilation system, like we talked about previously, where you have a fresh air vent coming into the HVAC system, you want to have that working and coming in properly in operating conditions. You will then take the measurement of the fan watt draw, or W fan, directly from the metering device. In the picture that you see on the right hand side, that's a plug-in meter. You'll be able to use this meter for an HVAC unit that actually has a plug-in outlet and not hardwired into the electrical system of the house. So basically you'll take the reading off the meter. If it is at hardwire systems, you would just have the other type of watt meter that basically hangs on the actual wiring of the furnace. So you will take that reading, and that is your watt draw from the actual furnace. We'll talk about what to do with that measurement in a sec after we're done talking about the other two methods. If you're going to be measuring the watt draw from the analog utility revenue meter, this is the setup. So all the registers again shall be fully open. The air filter shall be installed. You then want to go to the breaker panel and turn off every circuit breaker except for the one exclusively serving the air handler. So everything should be turned off except for the main, obviously, and the one connected to the air handler. Again, you'll turn on the system fan at the maximum speed, which is the cooling speed, like we talked about plenty of times before. And again, include the outdoor air introduction if the ventilation is provided through the return duct system. You will then want to go to the utility meter outside, the analog utility meter. If you look at the utility meter, you'll see a number with a KH somewhere on the particular meter. In the picture that you see here, the KH is found on the bottom right hand side. For the most part, that's where you'll find it the majority of the times. But nonetheless, if it's not located there, just look for a number that has the KH designation next to it, and that'll be your KH factor. You will then want to count the number of full revolutions on the meter wheel over a period exceeding 90 seconds. So when we talked about earlier, you needed to have a stopwatch, and that's what the stopwatch is for. So you're always going to count full revolutions, but no matter what, you have to count for at least 90 seconds, the number of revolutions. You want to record the number of revolutions and time period used during the count in seconds. So it has to be at least 90 seconds. It can be more than 90 seconds. You want to record the number of revolutions, always in full numbers, not decimals, not percentages or fractions of it. And then you want to record the number of seconds that you use to measure those revolutions. You will then plug in those numbers into this particular formula. So you're going to compute the air handler watt draw using the following formula. The W fan, which is the watt draw. The formula is going to be the KH factor that you got from the actual utility meter. So in our case, it was a 7.2 according to the picture that we saw a couple of slides ago. Times the NREV, which is the number of revolutions that you counted, times 3600. 3600 is going to be a constant. That 3600 is never going to change. Divided by the time in seconds that you use to count the revolutions, which is the TREV. And again, this is what the variables stand for. So W fan, again, this is the air handler fan watt draw, which you're trying to measure. The KH is the KH factor that you grabbed from the utility meter. The NRev is the number of meter revolutions, and remember, whole numbers only. You're always going to round up if need be. And then TRev, which is the time used to count revolutions, and again, always in seconds. And this is the example that we're going to use on the variables associated with it. So the KH factor is 7.2 from the utility meter. We counted 3 revolutions in 90 seconds. You will then plug in our numbers. So we have 7, which is 7.2 rounded down, times 3, the number of revolutions, times 3600, which is a constant number always plugged into the formula, divided by 90. So that gives us 75,600 divided by 90 seconds, which gives us a watt draw of 840 watts for that particular scenario. And that's the number that you would use moving forward. After you're done recording the watt draw that you just calculated, please remember to return all circuit breakers to their original positions. You don't want a homeowner calling you telling you nothing in my house is working because you forgot to turn them back on. So just go back to the breaker panel and turn everything else back on. For the digital utility revenue meter, it's very similar. So all registers shall be fully open. The air filter shall be installed. And again, you're going to turn off every circuit breaker except the one exclusively serving the air handler, just like you did for the analog utility revenue meter. And again, you will turn on the system fan at the maximum speed, usually the cooling speed. And again, include the outdoor air introduction and ventilation is provided through the return duct system, just like we did before in the previous methods. Here you see a picture of a digital revenue meter. So all you're going to do in this particular scenario is read the watt draw from the digital utility meter digital display. It's going to give you the number directly. You then will return all circuit breakers to their original positions. Now that we have both our numbers, we can actually figure out whether the system passes or fails. So there's 2 steps to determining that. First of all, we want to figure out whether the amount of airflow being pulled from the system, from the return system, actually meets the specifications based on the tonnage, on the AC tonnage of the system. So in our previous examples, our measured system airflow rate was 1600 CFMs. We know that the tonnage is 4 tons. Keep in mind that for the adequate airflow, it always has to be 400 CFMs per ton. So all we're going to do is we're going to divide the 1600 that we measured, and we're going to divide it by the number of tons. And that gives us 400 CFMs per ton. So in this particular case, we know that the system does meet the forced system airflow requirement. In order to determine the forced air system fan efficacy, we're going to compare the actual system airflow of CFMs with the watt draw that we measured earlier as well. So this requires simultaneous measurement of the system airflow rate and watt draw as previously described. In this particular example, the watt draw is 600 watts and the airflow rate is 1800 CFMs. All we're going to be doing is we're going to be dividing the watt draw divided by the airflow rate, which is 600 watts divided by 1800 CFMs. That gives us a fan efficacy of 0.33 watts per CFM. So the measured value for the fan watt draw shall be divided by the measured value for airflow rate to determine the fan efficacy. So the fan efficacy for this particular scenario is 0.33. If you look at the CF1R and the CF1R tells you that the fan watt draw is required, it will give you the target of what the fan watt draw fan efficacy will be. The number that you measured cannot be more than the target numbers in the CF1R. So by default, the fan watt draw for a system is 0.58 per CFM of fan efficacy. So in this particular case, it's 0.33. In this particular scenario, if 0.58 was the target, 0.33 is the actual measure of fan watt draw, that would be a pass. Now keep in mind that 0.58 is the default and is the prescriptive standard. Nonetheless, the number could be different. So always refer to your CF1R applicable to your project for this target number.
So now that we know how to collect and calculate the data for both airflow and fan watt draw, let's look at the compliance criteria. So in order for the system to comply with either the system airflow requirement or the fan efficacy requirement, the following criteria shall be met. So the system airflow, which is CFM per ton, shall meet or exceed the system airflow compliance criteria specified in the standards or on the certificate of compliance as applicable. So we have two different targets depending on what type of duct system it is. So the standard design for a traditional system is 350 CFM per ton, and for a small duct high velocity system, it's 250 CFM per ton. So these are both of the standard design or prescriptive requirements. If the performance modeling was used and we need to look at the certificate of compliance to verify that there's a value other than 350 or 250, here at the bottom is where we would find that. So if you open the PDF of the CF1R, you'll scroll down until you get to the HVAC cooling HERS verification section, and there in column number 3 you will see the airflow target. This one does just happen to be the standard design for a traditional system, and so that's what we would be comparing to. We need to be equal to or better than that value with our airflow result. The calculated value for fan efficacy, which is watts per CFM, shall be equal to or less than the fan efficacy compliance criteria specified in the standards or on the certificate of compliance as applicable. So again, we've got some standard design targets, and these are maximum targets, so yours needs to be equal to or less than the values here. And so we have 3 of them. So we're going to see 0.45 watts per CFM for gas furnaces, 0.58 watts per CFM for air handling units that are not gas furnaces, and 0.62 watts per CFM for small duct high velocity systems. Now these are again your prescriptive standard design targets. If the performance method was used, we're going to need to look at the CF1R to verify whether or not they used that standard design. So we're going to open the PDF, we'll scroll down until we get to HVAC fan systems, HERS verification, and there in column number 3, we're going to find the required fan power in watts per CFM. And in this example, they did use the standard design of 0.45 watts, and so we need to be equal to or less than that value in order to be in compliance.
Also keep in mind that depending on the type of system you're working on, you're going to be testing it in different ways. So for single zone air distribution systems with multi-speed compressor systems or variable speed compressor systems, but regardless single zone, you want to shell verify the airflow and the fan efficacy for system operation in cooling mode at the maximum compressor speed and the maximum air handler fan speed. There's going to be different ways you test single zone versus multiple zone systems. So we're going to be covering multiple zones next. If you have a zoned air distribution system, as I had stated, you shall meet both the airflow and fan efficacy criteria in every zonal control mode. Multi-speed compressor system or variable speed compressor systems shall only be required to verify airflow and fan efficacy for system operation in cooling mode at the maximum compressor capacity and maximum system fan speed, with all zones calling for conditioning. Keep in mind that in that particular scenario for the second bullet, that only applies to multi-speed compressor systems or variable speed compressor system as well. So how do you determine whether a system is single zone or dual zone or multiple zone? And these are some of the items that you can look for to realize whether it's a multi-zone system or a single zone system. So first of all, you're going to see motorized or actuated zone dampers on the supply ducts. You're going to see multiple thermostats or temperature sensors in an area served by a single system. So you're going to have one HVAC system but multiple thermostats. You're going to see a control board on or near the air handler with low voltage wires going to the thermostat's temperature sensors into each damper. So you're basically going to see the control board that goes to the individual dampers, and or you're going to see a bypass duct and a damper to the bypass ducts. Those are all good indications that you're working on a multi-zone system. And this is an example of motorized or actuated zone dampers on the supply ducts. Multiple thermostats or temperature sensors in the area served by a single system. a control board on or near the air handler with low voltage wires going to the thermostat and temperature sensors and to each dampers. You're going to see a board like this, as you can see, mounted near or on top of the furnace, and multiple wires going through different dampers. And then a bypass duct and or damper. And you can see here you have a bypass duct that's going from the return plenum to the supply plenum. Obviously a really good indication that that is a zone system. This is a diagram that shows how a zone system actually works. So you have a single air handler with a supply plenum, and then you have the supply ducts, the main supply ducts that go to 2 different zones. On the left side you have zone 1, and on the right side you see zone 2. In this particular example, only one zone is calling, meaning that only one thermostat is turned on, and it's actually calling for air to be supplied to that area of the house. So the zone 2 damper stays closed, and the air handler would only serve the area that's connected to the first thermostat or zone 1. So when we talked about the only way to test single speed compressors is to have all zones calling, you basically want to have all the thermostats on to cooling. Therefore, all the dampers will be open and the system will be servicing the whole house at once. When a zonally controlled forced air system is installed, the following shall be verified to determine compliance. And we're talking about visually verified. You have to visually verify that these items, either one of these items is present. So 1, a visual inspection shall confirm that bypass ducts that deliver conditioned supply air directly to the space conditioning system return duct airflow are not used, or if the certificate of compliance indicates an allowance for use of a bypass duct, the bypass duct shall conform to the specifications given on the certificate of compliance, and that is the CF1R. So basically, the CF1R will tell you if bypass ducts should be used in the system or not. If they're not supposed to be used but they're present, it will be a fail. If they are supposed to be used but they're not present, it will also be a fail. So you have to visually verify whether they are there or not and install to standard depending on what the CF1R states. For multi-speed and variable speed compressors, if this type of compressor is modeled, it must be installed and verified. Again, the CF1R will tell you. There are several features that indicate that a condenser is multi-speed. Product tags, labels, and marketing names that indicates 2-stage, dual-stage, multi-stage, etc. 2 compressor observed by looking down through the condenser fan, or high and low capacities or nominal tonnages indicated on the nameplate. The only definitive way to determine if the condenser is multi-speed or variable speed is to record the make and model number and find the manufacturer specifications.
Now let's take a look at central fan ventilation cooling systems. So what is that? This is where you will have the HVAC system act similar to what we call a whole house fan. We talked about this a little bit in the Title 24 section. Whole house fan, you open all the outdoor or all the windows to the outdoors, and you turn this fan on when it's cool outside. This fan will draw cool air in through the windows into the home, and then exhaust that air into the attic and then out through the attic vents. Well, a central fan ventilation cooling system does just the opposite. It's going to use a duct that goes to an outdoor inlet, so it's going to have access to the outdoor air. And again, when it's cool outside, it's going to use the return side of the duct system to draw this cool air from outside into the central system, and then it's going to distribute that through the ductwork to all the different rooms. Again, you're either going to have to open your windows or have some kind of a damper system that has outlets up into the attic. And so it's going to bring cool outdoor air in, distribute it through the house, and it's going to cool using that instead of a mechanical means such as the compressor and AC system. So when you have one of these central fan ventilation cooling systems, it's going to be using the blower motor for that air handler. We're going to have to verify that that watt draw of that air handler it meets or is better than the target value that we'll see that when they model it. Now this is a performance only, so you're not going to have any prescriptive requirements on this. You're going to look at that performance CF1R, define what the target is, and you're going to measure it using the same methods as what we used for verifying just the regular airflow and fan watt draw. You're going to do the same thing, but now you're going to be doing it in ventilation speed. So in order for these central fan and ventilation cooling systems to comply, there are two requirements that must be met. The first is that the system airflow, and again this is in CFM per ton, shall meet or exceed the system airflow compliance criteria specified on the certificate of compliance at both the high fan speed and the ventilation fan speed. And these are going to be different. High fan speed is just like what we're doing on any other standard HVAC system, but when it's a CFVCS, we're going to do both the high fan speed like normal, and then we're also going to do the ventilation fan speed. In addition to that, the calculated value for fan efficacy, which is the watts per CFM, shall be equal to or less than the fan efficacy compliance criteria specified on the certificate of compliance at both the high fan speed and the ventilation fan speed. So really the only difference for these types of systems is that you're going to be doing the same airflow and fan watt draw test that you did at high fan speed for normal AC systems. You're going to also be doing that a second time, and the second time is going to be just with the ventilation fan speed. So you're going to have two sets of results, one set of airflows for high fan speed, one set for ventilation, and then one set of fan watt draw numbers for high fan speed and one for ventilation fan speed, and these are going to be compared to their corresponding values from the certificate of compliance.
And now we're going to be mentioning the forms used and associated with the test we just talked about.
The CF3R MEC 22H is the verification form for fan efficacy or fan watt draw. And the MEC 22A version is for the all zones calling only method. It's 2 pages long. The MEC 22B variant is for every zonal control mode and is 3 pages long.
The MEC 22C is for all zones calling, but this is for a CFVCS system. So just like the MEC 22A, all zones calling, but this one has some additional information for those CFVCS systems. And then the MEC 22D is for every zonal control mode, but for CFVCS systems. Again, like the MEC 22B, but this one is for the CFVCS.
The CF3R MEC 23H is for space conditioning system airflow rate, and the MEC 23 variant A is for the all zones calling only method. It is 3 pages long. The MEC 23 variant B is for the every zonal control mode method and is also 3 pages.
The MEC 23C is for when it's an altered system and they only need to verify airflow for refrigerant charge, and they are unable to achieve the 300 CFM per ton needed for that verification. This is when the contractor is then going to use the remedial actions to try and improve the airflow. So this is where they're going to document the results, and you're going to verify that the appropriate remedial actions were performed and pass or fail the verification.
And finally, the MEC 23D is for systems that are not cooling, but you still need to measure that airflow when you have a CFI system installed. It's the all zones calling only, measurement only system and is 3 pages.
The MEC 23E is for all zones calling when you have a CFVCS system. Just like we had on the MEC 22, we have special forms for these CFVCS systems. And then we have the MEC 23F for every zonal control mode, again for those CFVCS systems.
If you have any questions about anything that we talked about in this PowerPoint, feel free to call us, leave us a message through the messenger system, or write us an email.